In the last lecture, we saw arithmetic code, uh, which gives us a scheme that can take as input any distribution Qn on any distribution Qn on n length sequences and give, so it can take as input any distribution Qn and give as output a code with code word length for the code assigned to the sequence Lx as log of 1 by Qnx plus 1. And in fact, it need not take the sequence um, completely. It just requires at each time t the probability of symbol t given all the past symbols. Okay? So it only requires a symbol by symbol access to this given the past. So given this, it can yield a code like this. So that's what arithmetic code does. And therefore, given a probability assignment, Qn of x, arithmetic code gives a scheme with average length summation over x p and x. So this is under p, average length under p, average length less than equal to this log 1 by q and x plus 2, and this, if you remember, can be written as d p and qn plus n times hp plus 2. Okay, so in particular it's roughly this much more, dp and qn, more than the optimal length nhp, and we would like to see how small can this excess, this redundancy in the scheme be made for any given p. So in the worst case p, how small can this redundancy be made? And and the qn that we would like to choose is the one which minimizes this. So we want to choose, not that we can choose it, we want to choose a qn that minimizes the worst case cost, max over p over all distributions in x, max over p min. So we choose the qn that minimizes this worst case redundancy d p n qn. That's what we would like to choose. Further, there is a practical concern. Further, we should be able to efficiently compute qn of xt given xt minus 1. Okay, note that if you have to remember this entire context xt minus 1, it will require a lot of memory as t increases. So ideally, we should not the scheme, we should not be required to remember the entire sequence, the entire past xt minus 1. Okay, so ideally we should not be required to remember this. That's the kind of scheme we are looking for. Okay, and so in this lecture, what we will see is how to come up with such a probability assignment. And in fact, that we'll give a family of probability assignments, and what we will show is that that I mean, we will not show this, but this family is almost close to optimal in the sense of this min-max cost. Okay, so here is our family of assignment. Before we do that, we restrict to binary alphabet. Okay, so we restrict to compression of binary sequences. Restrict to x equal to, let's say, 0, 1. That's what we will restrict to now. For simplicity, same ideas can be extended to general x. Okay, so what is our assignment? We use a so-called Bayesian heuristic and assume that the sequence sorry about this. Xn was generated from IID, independent and identically distributed, each symbol xi, Bernoulli P, where P, so now this is the Bayesian part, where P itself was distributed uniformly between 0, 1. Okay, this is just some strange assumption we are making. Okay, and that's the probability distribution Qn that we will use. That is, Qn is given by, let's say, Qn of x is given by first generating P uniformly over 0, 1, and then taking n independent samples from Bernoulli P. So there are two remarks here. First is that note that this is nothing to do with the actual process which was used to generate x. When we will use the when we will compute the average length, we will compute it with respect to some IID distribution. So this is not the distribution. It is some fictitious distribution we use for our probability assignment. That's the first remark. Second part is that this distribution actually is not IID distribution. It is a mixture of IID distribution because this parameter P, given P, these samples are independently generated and identically distributed, but the P itself is uniformly distributed. So the final distribution Qn is a mixture of IID distributions. But it's a reasonable guess actually, and it has a rich history of using this kind of prior P. Assuming, so suppose you don't really know what the bias of a coin is, it sort of makes some heuristic sense to assume that the bias is uniformly distributed. Although I'll mention later that this uniform distribution is not the best choice of P for our application. Okay. Okay, but it's quite good. So let's try to compute this probability Qn from this distribution Qn of, let's say, x t plus 1. What's the probability that this guy is 1 given the past? So you have already seen x1 2. You have already seen that x1 equals to x1, x2 equals to x2, xt equals to small xt. So we use base rule and write it as probability under Qn of xt plus 1 equal to 1 and xj equals to small xj for j between 1 and t, divided by Qn of xj equals to xj for j between 1 and t. So this is just base rule. And now to see this probability, given a p, given a parameter p, this probability is just look at the number of times 1 occur in this sequence. So p to the power k plus 1 and 1 minus p to the power t minus k. This is given p, but p can be anything between 0 and 1. So we integrate this over 0, 1. Divided by, I'm just computing both these probabilities, integral 0 to 1 p to the power k 1 minus p to the power t minus k dp. Okay, where k equals to number of times you see 1 in x1 to xt. So it's summation j equal to 1 to t xj. Okay, so this is just the number of ones in this sequence. Okay, so that's what you get. So now we will simplify these integrals. So we can note that the integral 0 to 1 p to the power m 1 minus p to the power n dp. So we'll do integration by part, and then we'll observe that this is nothing but integral n by m plus 1, and this guy increases by 1 and this guy decreases by 1. So you keep on repeating this procedure, and finally you will have all the power on the first guy minus 1 by m plus 2 and then this final guy is 1 by m plus n integral 0 to 1 e to the power m plus n dp. So what's this final integral? By the way, this guy here can be written as n factorial by m plus n factorial to m factorial. And then you have another so this guy can be written as n factorial by n plus m factorial, and then you have another integral here, so this is 1 by n plus m plus 1. Okay, so that's what we get for this guy. Now here we have ratio of two such integrals. So when we substitute everything, we note that thus for our assignment Qn of xt plus 1 equals to xt, is equal to 1, probability of 1 under your distribution, given that in the past you have seen x1 to xt is equal to k, that's the number of ones in this sequence, plus 1, you can verify this, just taking ratios to these things, by n plus 2. Okay. Okay, so this is a very interesting estimate of probability. Note that a more natural estimate of probability of 1 here, we were not supposed to estimate probability anyway, but a more natural assignment of probability would have been k by n. K is the number of ones that you have here, and n is the total, this should be t, sorry, k by t, t is the total length here. But what we seem to have done is, we have added 1 to all the occurrences. So this is k plus 1, this is the number of ones. How many zeros are there? Well, the number of zeros is t minus k, but we add 1 to it also. So this is like the empirical estimate, except that we have added 1 to all the occurrences, number of zeros. So this is number of zeros in xt, and this part here is number of ones in xt. So, and this whole estimate here, this guy here, is empirical estimate after adding 1 to each frequency. And the point is sort of that this k, suppose you choose the estimate k by t, what do you do when there are 0 ones? If you see a sequence of all zeros, will it be reasonable to call the probability of 1 zeros when t is small especially? And this estimate says, well, maybe I should put some doubt on the fact that the probability is 0. So I'll just add 1. So it would, if there are 0 ones on day 1, this one will, on t equal to 1, this one will still give estimate of 1 by 3 for probability of heads instead of 0. Okay, so this estimate has a name, it's very famous, goes back hundreds of years. So this probability assignment, why am I calling it an estimate? Because it's like I've seen this sequence and I'm thinking, what's the probability of one, the next one? Okay, that's what I'm viewing this guy as. So this probability assignment is called the add 1 estimate. Okay, and in general we can consider the add alpha estimate can consider the add alpha estimate for some alpha greater than 0 which correspond to a different prior, which correspond to a different prior on P. You can show that, but we don't even have to worry about how we came about how this estimate came about. We can just plug it in. By the way, this uniform prior that we use on P is sometimes called the Laplace prior, because Laplace used it in coming up with some estimate. And in general, we can use add alpha. The add half prior, we add half estimate. So instead of 1, if you add half here and half to each of them, so it will be k plus half by t plus 1 is known to have the best performance for the probability assignment problem. Okay, I'm not quantifying what I mean by best, and it corresponds to a specific prior. So-called Jeffreys prior. Pen is not working well today, sorry. So this corresponds to Jeffreys prior. So what does Jeffreys prior says is that the probability, okay, of P, so this is the prior probability of P, is chosen to be proportional to 1 by square root P into 1 minus P. Okay, instead of uniform, we choose it proportional to this. Okay, so it gives sort of higher mass to P around 0 and P around 1. Okay, instead of keeping it uniform. And that's very strange. Why would we give, if we don't know anything about P, why would we still bias think this way? And there's a rich theory of Bayesian statistics which justifies this. But heuristically, what you can see is that the difficult case is when the probability P of 1 is very small, because you may make a mistake and assign that probability to be 0, but in fact, eventually you will see 1 and it just have to wait enough. So you would like to put some mass there. So this guy says that this guy puts extra emphasis on this P being 0 or 1 and asks you to put some extra mass on that part. Okay, that's how you interpret this. Okay, but there is some theory which will justify this Jeffreys prior as the least informative prior, and this is for the binary case. In general, for a general alphabet, this Jeffreys prior is generalized by something called Dirichlet prior. Okay. All right. So we have this add one estimates and add half estimates. Let's just work with add one estimate. So what guarantees do we get from this add one estimate? Okay. So let's see what is the divergence between um, what is the divergence between Pn and Q for this add one estimate. To do that, let's first figure out this probability assignment. So consider a sequence xn with k ones. So this is a sequence of length with k ones, and obviously n minus k zeros. So consider the sequence. So our probability assignment Qn of x is the following. So let's take some. So we would like to write an expression for this probability assignment. So let's take some examples. Okay, some examples to build heuristic. So what is for our probability assignment Qn of, let's say 0, 0, 1, 0. So first we do Q0, then we do Q of, I'm just dropping this in, 0 given 0, then I do Q of 1 given 0, 0, and then I do Q of 0 given 0, 0, 1. So this first one is Q0. So let's do add half, add 1. So this is 1 by total is the symbol length is now, yeah, actually this one currently sees nothing in the past. Okay, nothing has been seen. So we are asking what q would put to this guy. So k is 0 and t is 0. So that's just half. Okay. Now this first guy has been seen, 0 has been seen. So you see one symbol that t is 1 now. So that's the denominator is 1 by 3. But the probability of 1 was number of, or probability of 0 is number of times you saw 0, that's 1 plus 1, so 2 by 3. Similarly, this one, probability of, so now you have t is 2, so this is by 4, and the number of times you see ones before this is 0, so you still have, um, you haven't seen any one till this point. So the probability of seeing 1, the probability of 1 is k plus 1. So k is 0, 0 ones here, so it's just 1. And the next one now is, you have seen 3 symbols, so 3 plus t is 3, 3 plus 2 5, and you have seen 2 zeros. So the probability of the k for 0 that you put there is 2 plus 1, 3. Okay. So if you observe this carefully, what happens is that the denominator here keeps on increasing by 1 every time. And the counter for 0 starts from 1, goes to 2, and then whenever next time 0 comes, it goes to 3, and so on and so forth. The counter for 1 proceeds the same way. So the order in which ones and zeros come don't matter. This counter always proceeds in the same way. So in fact, if you check, you can verify that this q of 0, 1, 0, 0 is also the same, except that first we will start with 0 probability. Now a 1 comes. So you will increase the denominator by 1. The numerator, the counter for 1 starts. Now the second 0 comes. So the second counter for 0. You can check this. And then third 0, so counter for. Okay. So this is the same as this probability. Okay. Right. So from this observation, we can now write, this is just an example we worked out. In general, we can write Qn of x is, the denominator will be 2, 3, 4 to the length of x. So since x is an n length sequence, but this is just a 4 length sequence, I'll remove this n part here. So in general, Qn of the sequence x n with, let's say, k ones. So in the denominator, what you'll get is 2 into 3, blah blah blah, and you go all the way to n plus 1. And in the numerator, what you will get is, every time you see 1, the 1 counter increase by 1. So you'll get 1, 2, total there are k ones. So you will stop at k and multiply it with now 1, 2, there are n minus k 0, so you stop here. So this is equal to 1 by n plus 1 into k factorial n minus k factorial by n factorial. So that's 1 by n choose k. Okay, so that's the probability assignment, where k is the number of ones in Xn. Okay, so this is the probability assignment that we get. So let's now try to compute the divergence Pn Qn. This is equal to summation over x Pn x log of 1 by Qnx plus minus n times entropy of P. You can check this part. So this first term is just the expected value under Pn of log of. Now we can substitute this expression n plus 1 into n choose k, where k is a random variable here. It's the number of ones in the sequence x. So I'll write it as k of x. That's a random variable. Let me just keep it as k, where k is the random variable. Just note it here. Random number of ones in xn generated IID from P. Okay, that's what this k is. Okay, so what is this expression? N minus n times n. Okay. So this expression here, this guy here, we can just take out log of n plus 1 out. And plus we have expected value of n choose k, but remember this bound that n choose k is less than 2 to the power h of k by n. So when you take log, this becomes 2 to the power h of k by n times n expected value under Pn minus nhp. And now this is the calculation we have done before. If we take this expected value over Pn inside, this thing will only increase because h is concave, and expected value of the number of ones that you see under Pn is exactly np, so this just becomes hp, the binary entropy. So this is exactly equal to, this is less than equal to log n plus 1, just like we did with method of types proof. So great, so we have already said that if you came up with a probability assignment, this is true for every p, so also for the max NP. So if we came up with a probability assignment, then the scheme that we have has redundancy at most d of p and qn. If we just plug this probability assignment into the arithmetic code, and note that the computation is very easy. We only need to maintain the number of ones and number of zeros that we have seen. So number of ones and the length of the sequence. That's all you want to have to remember in this scheme. Okay. So you can compute those probabilities, and it will give you this excess length over the optimal length. Forget about this plus 2. We are happy to ignore this extra 2 bits for n very large, let's say 50, 60 or even larger. And this guy here is just log n. So we get the same performance as type-based scheme. In fact, if you remember, I said that the performance analysis of type-based scheme can be improved to a factor of half. So you can have half log n plus 1 if you do a more careful analysis. Similarly, here, if instead of add 1, we use add half estimator, that's the best one you get, then you get half log n plus 1, which is optimal. Okay, so add half estimator is optimal. So add 1, the calculation was slightly easier. You can also try to use you can try to do the add half calculation. Okay, that's all I wanted to say in universal coding. We have actually given you finally a scheme which you can implement. The only thing that, well, a very important thing that you cannot implement about the scheme is that the arithmetic code, the way we have described it, will require infinite precision, and that obviously cannot be guaranteed because the intervals will become smaller and smaller, so you have to do very last decimal place calculations, and therefore there are many variants of the scheme which do not require infinite precision, which are used in practice. For example, you can look at redundancy if you insist on using a finite state machine which uses a fixed number of states, say m. Okay, then how much extra, then how much over NHP will you go? All these kind of analysis has been done. A lot of this work came out of, I think, IBM research, and a lot of this work was done by statisticians, information theorists, and there's a large body of literature. Finally, it all made it to different compression standards that we see around us in this class of compression schemes called entropic compression scheme. Okay, all right. So this ends our discussion on entropic compression, and this ends this unit 10. After this, in the same week, in this week itself, I'll continue with this unit 11, where I'll present a very different kind of compression problem, namely
compression of databases, compression to store data, where data you'll make queries to the data. Okay. That's what we'll do in the next lecture.